Hello guys, today I'm gonna show you how to create the pretty much realistic interactable water. It's not the water that you can achieve by adding water plugin in Unreal Engine version 4.26. It's actually, as you can see from the screen you are looking at, is the technique that was developed in version 4.13, and as you can see from the description, we will use render targets to create that fluid surface. It's the base we will take and make some addition changes because it's very basic setup. You can read through the whole description, not the description. You can read the explanation how it will work here on the website of Epic. The topic is called Creating a Fluid Surface with Blueprints and Render Targets. So here you can see the basic setup, as I said earlier, of the materials, also of the project and functions and the main blueprint. So if you want to understand the whole idea, you can read it here. In my video I'll explain in details only few things, and the things that will improve the basic fluid. And as far as you notice, if you look at the video and if you try to recreate it just by reading this information, you will notice that it's very basic, it's not pretty much expandable, and there are some features that are not supported. For instance, this tutorial you are looking at will only show you how to implement the interactive water with some line tracing on your actually using your mouse, but I'll show you how to create a component then you can attach to any actor, and if the actor is overlapping the water will react to it. Also, I'll show you how to make some fake raindrop splashes and add it to the weather system. Also, my tutorial will include such features that you can create a very big mesh. The scale can be very huge and the interaction will be correct during the whole mesh. I'm sorry guys that I'm making some very big pauses. It's because it's been a while, right after the Christmas, and I don't have enough practice in English. Also, I'm a little bit tired of making the tutorial, but please forgive me and let's get started. And we will begin with the post-process. It's called depth mask, and as you can see from the graph, we actually use the depth, the steam depth divided by the certain value, so we can subtract one element. Actually, we will have the radial mask, and we are subtracting one element by the width of our division from another. And as you can see from the preview, when we are actually changing our distance, the object is disappearing or appearing if we are getting closer to it. Make sure to select material domain as post-process and use saturate node, so our scene depth will be normalized between 0 and 1. I'm sorry guys. Next, we can move to material splat. As you can see, blend mode is additive, shading model is unlit, and we have checked allow negative emissive color, because to simulate the water behavior, the wave movement, we need to have the amplitude from minus to plus, from negative to positive. Here you can see we have changes that actually not the same as covered in the tutorial I have shown you earlier. So what do we have here? We have world position, and we need to subtract the position of our splat, our splash, the position we actually are standing or where we will interact with our water. So subtracting our position and adding the result of division of render target resolution, will actually have the proper quality of our splash. Next, we need to mask the two channel red and green, because our plane is has only two dimensions, x and y, or u and v. Here we have three types of texture samples. As you can see, it's the parameter, because we will change it through our blueprint. The first one is called player capture. This mask will actually cover our player's movement, the water movement around our player. The rain capture is masked for the raindrops, and impact capture is for other objects that are in area of effect of our water. For instance, if we are looking at the ball which will fall into the water. We are masking red channel and use power by 5000. The value is the same as we have in depth mask, so the reason we use the same power is for actually covering the proper mask, the proper object that we need to show the waves on our water. And we are subtracting from from the 1, the value we have here, because the scene depth actually is measured between 0 and 1. So next we need to saturate it to have the normalized version and multiply it by the player splat. These attributes, actually all these attributes, player splat, rain splat and impact splat, We need them here, but you don't need to change the values. Just set it to 1 for the default. We will change them also through our blueprint. And we will multiply it by 0.0001. So we'll have, actually it's for the usage that you don't need to change the player splat or rain splat or impact splat in your blueprint with some little values. You will need to go, for instance, from 1 to 100 and so on. It's much more easier to use the whole numbers instead of using such low numbers. So for this we need to multiply it by such a number. And as you can see, we are actually adding the same computations to all our masks. The logic is the same. Then we are adding all of them so we can have the whole effect together. And we are divided by 3 because we have 3 masks. So we won't have enormous artifacts when we will actually draw material to our random target. Next, we can go to high simulation. Well, shading model unlit, allow negative emission color selected. Same, not actually the whole same. Here we have additive because these masks will actually be multiplying or adding 1 by 1 each frame to simulate the water movement. And here, just make sure to have selected shading model to unlit and allow negative emissive color. Well, this setup actually looks the same. If you have followed my tutorial series, you can see that it looks like that we are going to have the outline effect. So we have 4 sides, left, right, up and down, and will actually cover our splash from all the sides. And the high simulation material is used actually to simulate or to be written the information from our blueprint that we have the movement of our waves. Textile size, as you can see, has very small value because higher values actually leads to very big textures of water splashes. We don't need it. All these attributes, actually all the attributes in whole our tutorial, not only in this material, also here and here, we will use them in our blueprint. Instead of using material instances, we can actually use different blueprints. Each will have unique values, so you don't need to create big amount of instances, and in case you have accidentally changed one value in material instance, it will actually change all matches that use this material. You don't need it. We will only use blueprints to have the full control over each water surface. So, back to our material. So, what do we have here? We have previous height, it's the texture. We will write through our blueprint the information of our movement, and by adding all these elements we will have the whole picture of our splash. Then we need to subtract the result of this computation by this. Next, multiply it by wave speed. Wave speed is for actually how fast our wave splash will spread through our surface. Next, we multiply it by 0.5 and subtract another texture sample, its previous height underscore 0.2. Actually, this is our first frame, this our next frame, and when we subtract one from other, we can actually have the movement. Also, we use multiply by dampening. This attribute actually is for telling how fast the water splash will actually move. Not cover our water surface, but the movement inside the wave we have created. So, take a closer look, or you can recreate it by reading the tutorial. I only show you the way how to make it look more easier to read. Next, material compute normals. The same layout, pretty much the same. Shade the model unlit. Negative emissive color checked. But with little differences. As you can see, we have another type of texture. It's called height normal. We do pretty much the same as we made in material height simulation, but if you take a closer look, here we don't actually need to follow the order what to add, but here to achieve the proper normal look, the blue one, we need to append the sides 1, 0, 0, 1 together, and sides minus 1, 0, 0, minus 1. This and this. Next, we need to subtract them and multiply by high scale to have actually the height of our wave. Next, we need to mask our channels red and green and make these computations. Make sure to follow the order of pins. I have them crossed only to have the pretty look. This one is for red channel, this one is for green channel, and then we need to have the cross product of other vectors and normalize them to have actually the normal of our wave. Using multipliers is for centering our normal map. Now to material of our base water. I don't pretend to create the very realistic water. It's actually pretty much simple setup, but for my purposes, I like it most. So near color and far color we are lampened by Fresnel, the default value, so we'll have the radial gradient from light color, bright water near our player and dark one far from our player. Also, for the material, blend mode is set to translucent, two-sided. Also, screen space reflections checked, lighting mode set to surface translucency volume, and you don't need to apply fogging for my case, because it can actually add some instructions, I don't need it, and can make some artifacts. My project doesn't use, or actually don't have, pretty much more fog, so it's up to you to decide whether to go with fogging or not. But you can actually create the volumetric particle and apply it on around your water to have more control and less instructions in your water material. Next, we need to divide our color by the depth fade to actually have the water line. So when the object is inside the water, the fade distance of depth fade will determine the size of the water line and go to the base color. For the metallic and roughness, same Fresnel, but you can see I'm lurking between two opposite values. So when we are looking right under our feet, we need to have some pretty much crispy metallic effect, and the roughness should be very low, so it looks like the polished glass. And when we are looking far from our position, material should be more gloss and less and has more roughness, so it will look a little bit flat according to the atmosphere effect. As for the opacity, I have this setup, Fresnel and depth fade multiplied together, and opacity here in Fresnel actually is for controlling the overall opacity. When we look right under our feet, the water is transparent, and when we look far from us, it should be opaque, not transparent. The depth fade here controls actually how much opacity we will have when we look near the area we are standing at. As for refraction, also Fresnel, and we are learning between 1 and 1.33. So when we look right under our feet and we are overlapping with our water, we need to have some pretty much disturbed effect. So goes for the whole area we are covering with the objects that are inside the water. And when we look far from our position, we don't need to see any refraction at all. As for the normal, pretty much the same setup we have here. Also we had in our compute normals, sorry, not compute normals, material splat, but with little differences. It's for the proper positioning and the proper size of our splash. So make sure that to follow the naming that you see here, so you can achieve the proper workable effect. As you can see, here I have the custom node. We have some HLSL code here. It's pretty much simple. We need to mask out the simulation when some objects are going to be out of our UV channel. So if the x is less than 0 or higher than 1, so we are out of the U dimension, or y is less than 0 or y is higher than 1, the same as for x, we need to return the floor 3 vector with 0, 0 and 1 values. So 1 is for the proper normal and 0, 0, so we don't see any movement on our mesh, on our plane of our water. If we are inside our UV coordinates between 0 and 1, we use 1 and 1 on x and y, so we can see the water effect, the wave effect of our water. And we multiply the result of these computations by the height normal, texture, and world position xy. We need to have the proper water tiling. And everything goes to our normal. So that's all for the materials. Let me go through everything one more time. Depth checker, material splat to actually draw the splash on our water, high simulation to write the information that our wave is moving, compute normals actually to have the proper visual effect of our distort water splash, and our water. Now we can move to our blueprint. Before we start with our blueprint, I'd like to note that I have the texture. It's called T_water splat, and as you can see, it's pretty much simple. It's 128 by 128, the simple circle with inverted radial gradient, the white inside and black outside. You need to create the same. You can use any, or you can just download it through the net. We'll use this texture to draw the effects of the water splashes for our local impact, when we are putting something to our water. Ball, sphere, cylinder, cube, and so on and so forth. Now, let's go to Common, and I have the Interactive Water folder. Here I have the Master Interactive Water, the Actor Blueprint class, and Scene component is the blueprint. Actually, when we use it on some of our actors or simple objects, when we add it to our object, then they can interact with our water. To start with our blueprint, first let's check the components setup. Static mesh is a simple plane from the basic shapes with no collision setup. Next, inside our static mesh, we have a child, it's box collision. Make sure that box extent is the half of size of your plane of static mesh. For instance, if static mesh size of a plane is 1000 by 1000, so box extent should be 500 by 500. Also, you can see that box collision has custom collision setup. It's query only and object type is set to water. Go to project settings and add inside the collision tab object channel, new channel, water, and default response is set to overlap. So for this, we don't need to line trace through something. We just need to line trace by the object type. It's much more easier. And default overlap for pawn and for other objects, so it will trigger the logic when we are stepping inside our water and it should respond. And inside our box we have post-process component. Unbound is unchecked, priority set to 100. It's for the proper blend between the global post-process and when we are when we are underwater. I didn't create the actual post-process for the underwater effect. I think I'll do it next time, but to have the proper look, just to see the difference, the white balance set to something small so we can have the blue color. Also, let me check. Exposure set to 1.4 by 1.4. Bloom set to 3. Actually, you can play around with this, with these attributes to achieve the look you would like to have. In my case, as you can see, the vignette intensity is set to 0.8. I don't like any lens flares or chromatic aberrations, but you can go with some of them. And the same level of as our static mesh, we have scene capture component. So the rotation should be set to -90 on Y and Z axis. The projection type set to orthographic. Make sure to add to post-process volume of our scene capture component. In post-process materials, the material we created earlier is the post-process for our depth test. This one. Also, in primitive render mode, we need to use show only list. So we'll actually only objects that are inside this list will affect our water and actually the information that we will write inside our render target texture. Capture source set to final color. Also, make sure that you have checked enable clip plane. If it's disabled and you cannot check it, you need to go to the project settings and inside rendering tab search for support global clip plane for planar reflections. We need this for proper behavior of our water. In case we will use planar reflection or just screen space reflections, but also for generating the waves. And in general, or actually in whole flags of scene capture component, you need to deselect everything but skeletal mesh, static mesh, and you need to have game line in post-process enabled. So that's all for the component setup. And if you can, as you can see from the construction script here and event graph here, it's all the logic. It's very compact and you can read through this blueprint very easily because everything is stored inside the functions. Each function has its own purpose. Let's actually go with the variables. We need to create the following list. Also make sure to have the proper name. For instance, in my case, height normal is written with the underscore because for some reason when I packaged my game and the name of this variable was height normal without underscore, the project simply, actually the content didn't cook because of some name issues. So, first of all, render target height 0, 0 and variable type texture render target 2D. This one also the same setup, actually only changes in names for height 01, height 02, height normal, player capture, rain capture, impact capture. The same setup, only different names. These render target textures are needed, so we will write information inside them and then use them in our material in compute normals, height simulation, and so on. So they will actually be inside the base water material, so we can see the movement of our waves. Next endpoint is the vector. We'll use this to designate the size of our static mesh of our plane. By default values are 100 by 100 and 0 on the x-axis. Make sure that default values here are the same, just for understanding the idea how we need to scale our plane. So they are the same size as our plane of our water. Next, near color and far color is the colors that we are going to change in our water. As you can see, this group of variables are set to be editable, so we can edit these attributes through the word outliner here. So for instance, if you have not only one instance of water but 2 or 3, they can be modified and have the different behavior and look. Next, opacity, depth, waterline, refraction. These are going to be the attributes we change, as I showed you earlier, in our base water shader. Make sure to provide the proper default values, so when you first time drag and drop your blueprint in the level, it will have some decent look. Next, simulation distance, dampening, wave speed, textile size, layer splat, impact splat, rain splat. As you can see, the names of these variables are the same that we have in all our shaders. Raindrop area, integer, and it's actually for faking the effects of raindrops on our water. The higher area is, the more area of water the raindrops on our water it will cover. Next, scene capture resolution, render target resolution, underwater height is the height of this box. So when we are out of this box, we won't have any effect of water simulated and any post-process. Next, scene capture, offset, and this is used with the clip plane of our scene capture component to actually I'm sorry guys, I'm a little bit tired. So when we subtract from scene capture component the value of scene capture offset, this value will, the result of this subtraction will actually go for the size of object of our player that is inside in our water, so we can capture our player inside the render target to write the information to shader to have the proper effect of the wave. Something like this. Next, material instance dynamic for height simulation, compute normals, splat, and water. As you can see here, we don't have any default values because I'll show you later. We will actually create these nodes that create dynamic instances of material, and these variables will be the references for those nodes. Next, height state and captured player. The variable type here is BP player character, in my case. In your case, it should be your player. It can be third person character or any kind of character you want to have. And with this setup, we can actually go first to the construction script. So, construction script. Set world scale 3D for static mesh. That should be 1, and we use endpoint vector divided by 100 to have the proper size. So the units of static mesh of our plane of water are actually have the size of 1, and when we change the value, the scale will be increasing. So next box, it's our box collision here. We use underwater height on z-axis and 1 for x and y, both for set relative scale 3D, and set relative location of the box 0, 0, so it's centered, it doesn't go anywhere, and on z, underwater height multiplied by -1, so when we increase the underwater height, it's actually be going right above our plane, downwards. Next, we create material instance dynamic with water shader we created earlier and assign it to the static mesh. It's our plane, and this material instance dynamic water variable, we store the return value here, so the reference now will be this variable, the reference of this material. And the first function here, prepare base water. So here we just set scalar, vector or texture attributes for all of our shaders with the proper values. So for material instance water, simulation distance, make sure that the parameter name here is the same that you have created in your shader, in all of your shaders, so you'll have the proper and workable effect. Next, near color, far color for water, opacity, depth, waterline, refraction. Next, this is for preventing the errors when you launch your level, and actually you don't need to create these material instances before the begin play event fires. So in case to prevent error spamming in the log, you need to check whether those elements are valid, and if it's so. Next, for the height simulation, we are actually changing 3 attributes: dampening, wave speed, and textile size. And for the compute normals, only textile size. So that's it. The purpose of this function is for visual feedback. So when you make changes here, the water will actually make feedback right in right in the moment. And when we're done here with our construction script, we can move to the event graph. Here you can see the overlapping logic. We need to select our box collision, scroll down to the bottom and add on component begin overlap and end overlap events. Then we use cast to our player character. So if it's true, we store the return value as the reference variable we created earlier. And from capture player, we need to get mesh. It's a skeletal mesh component or static mesh component. It's up to you to decide what you have inside your player. And we use show only component from scene capture component 2D, and we store the mesh of our player inside the show only list. And when we add overlapping with our box, we check whether actor is our player. So if it's so, we need to remove it from the show list, and we actually need to invalidate our player. Now, when we have this setup, let's go to our player character, and I'll show you some changes you need to add into your player to make it work. And as you can see here, I have the basic skeletal mesh from the tutorial. The reason for this is pretty much simple. To have something captured inside the render target to simulate the water effect, every time I say water, wave effect, you need to have any skeletal or static mesh inside. In my case, I'm using this skeletal mesh. I don't need to have the proper behavior for the legs captured inside the water, for the water, because I'm making the first person game. But if you have the third person character, actually all you need to do is to have the skeletal mesh and animation blueprint assigned in your player here. And actually that's all. And if you have the proper animation blueprint, when you look downwards, right under your feet, you'll see that it will capture the proper leg movement. So instead of having big splash that I have, you'll have each step captured, so the effect will be more realistic. So the idea of this interactable water is that it can be used for first-person character and third-person character. In case you have camera attached to the player character here, and you have animation blueprint here, you will see that your legs will actually be displayed and the effect will work too. In my case, to not show I don't need to show the mesh, but it should be captured, you can go to the details and check on the no see. So the capture will actually capture the movement, but your player mesh won't be visible. Next, event begin play. And here is another function, it's prepare render target for the height. And for the inputs, it's simple float, and we use render target resolution variable here. What we do here, we create render targets. We don't create them as the assets and store them on our hard drive. We create them virtually. And size is the same for width and height of render target. Also make sure that the proper type of render target is created with the proper format, so you won't have any artifacts. Next, we need to clear our render target, all with the black color. Next, we create material instance dynamic for high simulation shader, compute normals, and splat. Next, prepare capture render target. The setup for the function is the same, float, but here we use scene capture resolution as the input. Here we create another render target. Make sure to follow the proper format for player capture, for rain capture, and for impact capture. Next, prepare scene capture function. Here we need to drag or pull a wire from scene capture component and search for set texture target and apply player capture as the target. So when we will move, actually you will see it later, we will be capturing the area around our player. Next, simulation distance is set as the auto width of our scene capture component. So the higher value is, the more distance we will capture, and the more effect of wave moving, water moving with waves, we will see. Next, we need to set the clip plane on that axis for our scene capture component. So the higher the value is, the more body we will actually capture, and the waves around us will have bigger size. So select wisely. Next, we set scalar parameter for simulation divisor or divisor in our Splat material. Render target resolution, and we are setting textures, player capture, rain capture, impact capture. For the texture samples that we created earlier in our Splat material, make sure to follow the proper naming. And the last one is height normal in our water. So everything is set. Here we also fire prepare base water, the same function we have in our construction script. So this logic will fire, and we will have the proper values for the materials we create here. Next, we have the same part of logic that we have when we are overlapping here. In case when we are beginning our game, so if we are actually in the water, for instance, if we are in ocean and our gameplay is in ocean, we need to actually add our player before we are overlapping with our box. So we check whether we are actually overlapping, actually our player character is overlapping with the water. If it's so, we cast player character and store it as the reference. Then we add it to the show list. Next, on event tick, we check whether our player is valid. We need this to move our render target with us, not render target, the scene capture component with us. So, if it's true, we set world location for the scene capture to a new location, but we use actor X and Y location of our capture player, and that axis of actually scene capture component make new vector and assign as the new location. And then we fire another function, it's called apply splat. This function is used to generate waves around player. As you can see, the input is position, it's simple vector, and the position of our actually captured player. And in case we are out of our water, if there was some movement, we need to continue simulating it. So we need to skip the movement of our scene capture component and continue with wave simulation here. Now apply splat function. We also check whether our player is valid. If it's so, here we can see we use another function which is called get higher render target. Here we will have the proper render target we need to rewrite information to. So get high render target is a function that input has the integer and index. We check whether it's 0. We need to return texture render target to D. So if it's 0, we return this render target. If it's 1, we return this. If it's false, we return the last one. And the target height 0.2. So every frame we are actually manipulating these render targets to have the proper effects of the wave simulation. So back to our function apply splat. We check our height render target. Then we need to set vector parameters for splat position in our splat material and water material, so they are synchronized and the splash around our player will be in the proper position with a proper size. Then we use draw material to render target node and we draw the material splat inside the render target we have here. So render target now has information about the splash around us. Next we need to set scalar parameter of player splat. It's the size of the splash we are creating with our body inside material. This is dynamic splat. Now let's continue. Next we need to set the height state. It's the index we use for determining which render target of height we need to go with. And as you can see, each frame we are actually adding we're actually iterating through the indexes, then dividing them by 3, we setting them for the cycle. So we have the current state and some previous states, and it simulates their movement. Next, draw waves function. Here you can see we have another function. It's called get last height render target. It has current index, previous index, and height render target, which is texture render target 2D as the output. And let's go inside it and see what we have here. Inside get last height render target, we actually use this function, but we are actually providing the computation between current frame render target index and the previous one. We add 3 and divide by 3, so we have the proper render target as the return. So back to draw waves, we use get last height render target with current state, and previous index here is 1. Then we set texture parameter value for the height simulation material, the previous height underscore 01, previous frame. Then we use this function, but with the previous index of 2, and set the same attribute, but with the index of 0.2, previous height underscore 0.2. Next, we use get height render target function with current state and use begin draw canvas to render target. Next, as a canvas. Next, we use draw material. As a canvas, it's the return value of this node. Render material we are drawing into is the height simulation. For the screen size, we go with the screen size of this return value of this node. And as for the context, we need to add draw canvas to render target. So every time we are drawing, we need to end it, so we will have the previous behavior, the previous information. So simple. Next, right after draw waves, in the event seek flow, we use compute normals, and as you can see, it uses the same, pretty much the same logic. We get high render target, so we get the proper render target. We set it as the high normal texture attribute inside the compute normals material, and we draw material compute normals inside the high normal texture, and this will be used inside the water material. Next, we are clearing rain capture and impact capture render targets with the white color every frame, so ripple should show the ripples from the simulator will be cleared. Sorry guys. Next, the implementation for the weather system. So if you have followed my tutorial series, you know that I have the weather system. If you don't have it, you can skip this step, but if you have it, as you can see, it's the function that is implemented inside function library. All I do is get OLectr of class weather system, and because it's every time it's actually my level, and each level should have only one weather component, weather system, so I can use the 0 index to get the proper element and return it as the weather system reference. So inside my weather system, I check whether it's raining. If it's so, I apply another function, it's called apply rain splat. If it's false, you don't need to do anything. So every time it's raining, you will see the ripples on your water. Now, inside applied rain splat, we actually also check whether our captured player is valid. Next, we need this kind of logic. Our raindrop area is in units, and we actually use random integer in range 1000 and multiply it by -1, so each dimension has its own values from this operation. Next, we add the result. We actually make the int vector and convert it to the simple vector and add it to our player character location, so we'll have the area of effect around our player. Next, another function, it's called getLocalImpact, and we need this to calculate the screen position where should we draw the texture of our ripples. This one. And getLocalImpact, as you can see, I have the instigator location and relative location, it's two vectors, and as output is vector 2D for the screen position for drawing the texture on our render target. Instigator location is the location of our player and of our player. As for the relative location, it's the location of the screen capture component, this one. Next, inside this function, we actually make transform, then inverse transform location with the location of relative location. Actually, all we do here is we are manipulating the world values, the values of the world position, and try to recreate some kinds of UV position. So we are checking on which point inside our area of effect around our player we need to draw, as I said, our ripple. So all the transform around us, or the area, is like the UV coordinates from 0 to 1. So right after we have the inverse transform location, we need to divide it by this operation, simulation distance divided by scene capture resolution. Then we need to make x and y dimensions, or UV. We use scene capture resolution divided by 2 to have centered. So the center of our transform will be the center of our plane. Then we multiply it by -1 and make vector 2D. So simple. And back to apply rain splat, we use begin draw to render target and use render target rain capture. Use draw texture to the canvas here. As for the texture, we use water splat texture. Screen size is up to you to decide with what to go, but very high values will lead to distortion effect on your water. As for me, 3x3 is okay. Also, we need to end draw to render target and apply rain splat attribute to material splat dynamic with the proper parameter name. Rain splat is the strength of how much distortion our ripples will cause, will apply on our water. And that's all for the interaction water blueprint. Also, you can notice that we have left some functions. Actually, it's apply local splat. Let's implement it, and we will use it inside the water component here, the component that we will add to any object to have the impact on our water. So, apply local splat. We have impact point and impact size, vector and float as the inputs for our function. We also check whether our player is valid. If it's so, we use the same function we used earlier. It's get local impact, and for the relative location, it's the location of our actor. As for the instigator locator, it's the impact point we will inherit from the input of our function. Next, the same. Begin draw canvas to render target, and the texture render target is impact capture. The return value of get local impact function as screen position. Also, render water texture. Also, render texture is our texture of water splat. This one. But for screen size, we use impact size that we have from the inputs of our function, and we make vector 2 to have the proper ripple and feed it to the screen size here. Next, add draw to render target and set scalar parameter impact splat with the impact splat here inside our material dynamic of splat. So our water actually is disseminating the local impact will disseminate the size of the water ripple, but the overall strength of all impact that we are acquiring through our world to our water are set in the water blueprint. So when this is done, we can go to the water component and actually take a look. Interactive water is the reference to our interactable water. Trace distance is the height or the length of which our object needs to trace to get to the water, and when it's tracing it, we need to actually apply the function to draw the ripples. Impact size here is actually to determine the size of ripples we have from the local impact. This one. And heat is the simple structure of heat result, just to keep the blueprint clear. So what we do here, we check whether the order of our component is valid. So if it's so, we can actually go along with the logic. If it's not, we don't need to do anything. Then I need to line trace from the bottom of my object, not from the center but from the bottom. I use get owner and get actor bounds. Then I split the structures of these pins and make vector with x and y, so these values are changed, and then we need to subtract from the origin z, the box extend z, So this will be the bottom side of our object. Next, we need to multiply the trace distance by the vector of -1 on that axis and add it to the result of this computation. And line trace for objects. The start is the bottom of our object, and the end is actually the length from the bottom centered downside to the water. Also, I use make array and select water as the object type that we created earlier in our collision channel. Let me show you one more time, this one. So we line trace, save the result, then we break the heat result and check whether heat actor is interactable water. If it's so, we actually apply local splat function, this function, to draw the ripples on our water. Impact point is the location of our actor that handles or carries our water component, and impact size is the size that we disseminate in our wall outliner in the component of our actor. So everything left is actually to show you how it works. So as you can see, here I have the setup for my water, and I have 3 simple spheres. Actually, all I need to do is to add component, search for water component. Right now I have it, this, and this, and that's all you need to do to have your object be a factor on your water surface. And when you add the component, you need to select it. You can change the impact size of each actor that carries your component. So for small objects you can go with impact size with some small value, for big objects with bigger one, and line trace distance is up to you to decide with which to go along with. And as for water, change the values and see how it works. Also, make sure that textile size is set to small value. Here I go with the rule 1 divided by the period of 2, for simple 246, 2048, or 1 divided by 8192, or just like this by 4096. So it's pretty much, the textile size should be 1 divided by the size of the simulation distance you have here to have the proper effect. But you can go with some lower values to have less distortion on your water surface. Because simulation, when you increase simulation distance, it will increase the size of your water ripples, because the textile size doesn't change. So every time you change simulation distance, you need to change the textile size. Something like this. So I found myself useful using simulation distance as 4K and textile size 1 divided by 8,192. So with these values you can achieve the result I have in the demo right before I start this tutorial. Also make sure to change scene capture offset something high values in case you don't get any interaction with the water. And don't go with some high values on render target resolution. 1K or 2K is enough. Higher values leads to higher quality but to higher performance impact. Whew. And this all for the tutorial. I hope you will like it, and please forgive me my mistakes. Right after Christmas is very hard time right now, but nevertheless, if you like this tutorial, please feel free to leave your feedback, subscribe, and I'll see you soon with 2 more interesting tutorials. The one will be for the quest system, and the other is for actually grabbing and carrying the objects. So guys, see you soon.